Welcome to another podcast. This episode we're going to be taking a look at what are called saddle point systems or planar systems that have critical point behavior called a saddle. You're probably familiar with the term saddle from looking at some things in Calculus 3. And so I think you'll know where this term comes from when we get to it. But the system that we're looking at here is minus x plus 3y and then 5x minus 3y. Its coefficient matrix is given by this. And so hunting for the characteristic polynomial here, we get lambda squared, the trace is plus 4, and the determinant here is 3 minus 15, so it's negative 12. This factors into lambda plus 6, lambda minus 2. And so we have two eigenvalues here. We've got a lambda 1 as negative 6 and a lambda 2 is 2. These are our two eigenvalues. And what I want you to notice here is that these eigenvalues have the property that they are different in sign. So one of them is positive and one of them is negative. That's how this is different from the nodes that we looked at in the previous video, where both of the eigenvalues have a nodal system. Both of the eigenvalues have to be either both positive or both negative. So if we try to solve this for the eigenvectors, a plus 6i is the matrix 5, 3, 5, 3, so clearly it is redundant. This will generate the eigenvector 3, negative 5. And so I'm going to pair that with lambda 1, which is negative 6. And then if I look at a minus 2i, corresponding to lambda equal to 2, then the appropriate coefficient matrix there is negative 3, 3, 5, and negative 5. And so the alpha 2 value is going to be, let's see, 1, 1 works here. And our second value associated with that is 2. Alright, what this does is it leaves our solution x of t as being the following. And so we are in a somewhat similar situation to the node problem. There is sort of a significant difference here, and that difference is the fact that the eigenvalues have different signs. One's positive and one's negative, so it's going to make a big difference. If I look at t equal to 0, so if I look at c1 is 1, c2 is 0, and t equal to 0, then I'm looking at the vector 3, negative 5, so I'm at 3, negative 5, I'm at the tip of that vector. And as time moves forward, because it's e to the negative 6t, I'm collapsing into the origin. So this is the solution corresponding to moving forward in time with c1 equal to 1, c2 equal to 0. So this solution, the arrow would be pointing in. And so if I go ahead and extend that eigenvector going backwards in time, and going forwards in time. So let me extend it backwards in time. So backwards in time and then moving forwards in time. So backwards here would be negative 3 and 5 right there. So continue along that line right there. So on both sides here we're collapsing into the origin, and that's because the eigenvalue for this problem was negative 6. And we learned in the last video that if you have an eigenvalue that's negative, then it's creating things which collapse into the origin. Okay, similarly, if I look at the other eigenvector, it's 1, 1. So I'm here, and what's happening here is a little bit different. Over time, I'm getting further away from the origin. So this thing would look like this. So I'm getting further away from the origin, and if I go backwards in time, then I'm getting closer to the origin. So I'm basically emanating from the origin is what I'm looking at here, and it's the same thing on the other side. If I look at the vector on the other side, this would correspond to C1 or C2, excuse me, being -1 and C1 being 0. This is C2 equal to 1 with C1 equal to 0. But both are emanating from the origin. So we think of this as being a source curve because it's coming out of the origin. Well, what this means for our solution behaviors is we don't have to worry as much about which one dominates because you can clearly see kind of the reaction that's going to happen here. You're going to get curves that come in along this one, but they're going to get closer here, and eventually the red pulls them away. So you're going to get sort of this sort of solution behavior. Same thing here, solutions are going to come in along blue, but they're going to leave along red because red is going to be the dominant one moving forward in time. Same thing here. And then the same thing here, coming in from blue, leaving toward red. And so you can draw the arrows here along your trajectories to match what they are for the eigenvectors themselves. But what's interesting here is the only way that you make it into the origin on this problem is if you start on the blue curve. That's the only way that you reach stability. So yes, there is a stable solution here, but generally this is unstable behavior because you're never going to get settled looking at these trajectories. So if you look at what we have here in terms of the overall solution behavior, this is very reminiscent of a surface called a saddle in Cal 3, and it fits that description very well because saddle points, you have sort of this high point where everything funnels into it. So if you're at the high point, you fall off in one direction, you fall away. In the other direction, you're coming in. So the solution behavior here at the center point, so this solution has what's called a saddle point behavior, and you don't call it saddle point sink or saddle point source because it has both behaviors. That's what makes it a saddle. So the fact that this is a saddle behavior comes from the fact that one of the eigenvalues was negative and one of the eigenvalues was positive. And so it doesn't really matter which one was which, it just matters that they had different signs. And so you can see that you're going to end up with this sort of behavior for any of these problems where the eigenvalues are different in sign. There's really not much more to say about this one. This is a pretty easy solution behavior to spot. It's a pretty solution behavior. You see nice trajectories in the phase plane when you plot solutions to saddle point systems. But the behavior itself is not all that complicated. All right, thank you for watching.